So, it is my honor to introduce Chelsea Finn as the speaker for the next talk. Chelsea is an assistant professor in computer science at Stanford University right now. Chelsea's research interests lie in the ability to enable robots and other agents to develop broadly intelligent behavior through learning and interaction. To this end, she has developed deep learning algorithms for concurrently learning visual perception and controlling robotic manipulation skills, inverse reinforcement learning methods for scalable acquisition of nonlinear reward functions, and acquisitions of and meta-learning algorithms that can enable fast, few-shot adaptation in both visual perception and deep reinforcement learning. Finn received her bachelor's degree in electrical engineering and computer science at MIT and her PhD in computer science at UC Berkeley. Her research has been recognized through ACM Doctoral Dissertation Awards, an NSF Graduate Fellowship, a Facebook Fellowship, the C.V. Ramamurthy Distinguished Research Award, and the MIT Technology Review 35 Under 35 Award. And her work has been covered by various media outlets, including the New York Times, Wired, and Bloomberg. With Sergey Levin and John Schulman, Finn has also designed and taught a course on deep reinforcement learning, with thousands of followers online. Throughout her career, she has sought to increase the representation of underrepresented minorities within CS and AI by developing an AI outreach camp at Berkeley for underprivileged high school students, a mentoring program for underrepresented undergraduates across 3 universities, and leading efforts within the WIML and Berkeley WICSE communities of women researchers. And as a final note, I would like to say that Chelsea is one of the few people that have made field-changing contributions in more than one field. So it is a pleasure for me to introduce her. We are very happy to have her.
Thank you for the introduction. So today I'll be talking about some of my work and in general a broad overview of how we can enable robots to learn. And as was mentioned, I've worked both in the area of machine learning and the area of robotics. Today we'll be focusing more on applications in robotics and how we can enable robots to do things in the real world. So to motivate what I'll be talking about today, I'd like to start by discussing some of the most impressive feats in artificial intelligence. These include things like TD Gammon, IBM Watson, machine translation systems, DQN, systems that can learn to play Go. And these systems are remarkably impressive, and also many of them are very useful. And I would argue that they're very impressive because they can perform a very complex task very well, sometimes even better than what a human can do. For example, if you had a friend that could translate between multiple languages or was a champion at Go, you'd probably be pretty impressed with that friend. But at the same time, I think that we need to be thinking about what does intelligence mean? And in many ways, these systems are not necessarily as impressive as a human that can perform some of these skills. For example, the system that can translate between 2 languages doesn't necessarily understand the language that it's translating. It can't tell you a story in that language, and it can't respond to dialogue that you're telling it. And so I think we need to be thinking about how can we build not just systems that are very specialized towards these very particular tasks, but also systems that have basic understandings of the world and can do many different types of things. And so if we want to be able to do kind of a wide variety of basic things, what about thinking about artificial intelligence systems that can interact with the world, can manipulate objects, and perform various tasks in the physical world? Well, it turns out that simple yet general manipulation skills are beyond the scope of our current AI techniques. Even things like manipulating Go pieces are well beyond what we can accomplish today in a wide variety of situations. And this may seem counterintuitive. These skills look very simple, and things that are incredibly intuitive to us to accomplish every single day. So how is this the case? Well, it turns out that the simpler yet broader capabilities, such as interacting with the world, grasping objects, interacting objects, are really hard. And they're actually harder than the things that are seemingly complex to perform. And this is something that's known as Moravec's paradox. It's that the things that are so intuitive to us, we don't have an understanding about how we develop them ourselves. And as a result, it's very hard to actually build these systems into artificial intelligence systems. OK, so in this lecture, what I'd like to talk about is how can we bridge this gap? Can we build artificial intelligence systems that have that have the capability to interact with the physical world and learn basic motor skills. And it's worth mentioning that beyond kind of the motivation from artificial intelligence, from kind of the philosophical point of view, if we can build robots that are generally capable in a wide variety of environments, then first it will have a wide range of socioeconomic impact in terms of performing jobs that are dangerous and tedious for humans to do, driving cars and trucks without having the distraction that humans have, assisting in surgery, and a wide variety of applications that I think have the capability to really transform the world that we live in. Yet at the same time, I think there's also a number of potential harms in automation as well. This includes things like, job loss and worker displacement when jobs move from one location to another location where jobs are being created. And also, these newly introduced jobs that are created by technology may also require higher skill levels. And so I think it's worth thinking about both of the benefits and the potential harms of this technology. And for both of these reasons, I think it's really important to understand the capabilities and limitations of current robotic systems and current AI systems so that we can understand what these will look like in the future. OK, so an outline of what I'll be talking about today. First, I'll be covering some of the basics of robot learning, how we can set this up as a learning problem, and imitation learning techniques for solving it. Then I'll talk about model-based reinforcement learning, an approach that has been used to enable robots to accomplish a wide variety of different tasks, how we can extend these techniques to settings where you have image observations, and lastly, talk about my perspective on some of the open challenges in robot learning and where we stand today with regard to those challenges. OK, so first let's go over some of the basics. So as many of you are probably familiar with, object classification is one problem that we can solve pretty well with machine learning systems. And how does this compare to something like object manipulation? So in object classification, you can formulate it as a supervised learning problem, whereas something like object manipulation is inherently a sequential decision-making problem, where you're making decisions at multiple points in time. And so these two problem settings introduce different challenges. So in supervised learning, you typically assume that you have IID data that you can draw from some independent and identically distributed data set. And in contrast, in sequential decision-making, your action affects the next state that you see, your next observation, and so you can no longer have this nice IID data set. Second, in things like object classification, we typically can curate a very large and labeled data set, whereas in contrast, in reinforcement learning settings, we need to think about how we actually are going to go about the data collection process ourselves in order to learn, and also think about what is the form of supervision that we're going to be giving robots. These questions aren't immediately clear from the outset. And lastly, in something like object classification, there are fairly well-defined notions of success based on accuracy and how precisely you can make decisions or label images. Whereas in things like robotics, it's a bit less clear how you actually define what success looks like. OK, so these are some of the challenges that come up when you consider these types of domains. So first, let's go over some terminology before getting into some of the methods for actually solving this. So in a typical image classification problem, before we get into reinforcement learning, you might consider a setting where you're given an image, and you want to be able to predict the label corresponding to that image. Now, what changes in the context of sequential decision-making is first, instead of having a single image, you'll have the image be a function of time, and you'll be making decisions at every time step t. And second, the actions that you take at a given point in time will affect the next observation that you see. And your actions may be something like running away from the tiger, ignoring it, or petting it. OK. So you have these different actions that you may be considering. Typically, O is denoting the observation, A is denoting the action. And there's also this pi is your policy, is the function that you're using to make decisions. And there's also this notion of a state. And in particular, the state considers settings that are fully observed, where you can fully observe the low-dimensional state of the system. So for example, the observation may be something like an image, while the state might be the positions and orientations of the objects or of the agents in your observation. And so as you might imagine, if your input is something like the poses of these objects, that might be easier to deal with than if you have to handle the pixel observations in an image. And things may get a little bit harder if you have something like occlusions, for example, where part of your state is occluded by an object. And that would also be kind of considered a partially observable setting. OK, so what's kind of the first basic approach that we can consider for trying to solve this problem? Well, what we can do is we can take the same approach that we took in the object classification setting. So we could basically take a data set. So maybe we want to learn how to drive. Our observations are the images from some camera in our car, and the actions are how we want to steer the car. Then what we can do is we can collect a data set of humans driving, cars on different roads. We can then, containing both the observations from a camera as well as the actions corresponding to the steering angle, put this into a large training data set, and then run supervised learning and train a neural network or your favorite function approximator to produce the actions given the observations. And so as a result, you would get some policy that outputs a distribution over actions given your observation. So this is really simple, and is something that is pretty easy to apply to various sequential decision-making problems. It's known as imitation learning or behavior cloning, where your goal is to imitate the actions that you see in a data set. And does it work? At the outset, there are situations where it doesn't work. And the way that you can see this is you can consider an example where you have some training trajectory shown in black. And at the beginning, you may follow that trajectory very closely, but at one point you'll make an error because you won't be able to perfectly fit the data. And then when you make an error, you'll fall off that trajectory, and you'll see a state that's a little bit different from the data that you saw during training. And then you'll make potentially an even larger error because you're off of the data. And these errors will compound, and over time, you'll get a trajectory that diverges from the training trajectory that you saw. And so for this reason, imitation learning can be challenging because you're not actually reasoning about how to accomplish the right outcome. You're just trying to mimic the actions that you see. And as you make errors, you'll fall further and further away from the observations that you saw during training. That said, in some situations, it actually can work. So this is a paper by some folks at NVIDIA in 2016. What they did is they took a car, they drove the car in various different situations, including rain, including snow. And what they found is that with imitation learning, they were able to achieve 98% autonomous lane following using only 72 hours of data. And so in general, one of the things that we can find is that if you have a fairly large amount of data, and if you are able to fit that data well with a very high capacity model, such as a neural network, then you're less likely to make errors because you're fitting that data well. And the other thing that they did, and a number of other works I found to be very important, is to use data augmentation wherever you can do so. So for example, things like randomly shifting the image, randomly rotating the image by small amounts in ways that affect your action in predictable ways. The other thing that they did in this particular paper is have multiple cameras from different angles of the robot, and they could use that to augment their data set and say, if you see something that looks like the right camera, you should actually steer left, because that will bring you back on the road. And this can help get more data around the data density distribution, such that when you make mistakes, you don't quite fall off this very narrow strip of data. OK, so there are situations where imitation learning can work quite well. And in particular, some of the benefits of this approach is that it's simple and sometimes can be relatively effective. Of course, we wouldn't necessarily want to deploy that driving system if it only has something like 98% autonomy. In practice, we need something much more accurate than that to actually be able to handle or at least be able to perform at the level of humans. But it does work somewhat surprisingly well, given the simplicity of the approach. Further, with imitation learning, there's no challenge of exploration. You have the data that can tell you what to do in different contexts. There's also no need to specify a reward function for how to actually accomplish the task. You can simply just collect data of humans performing the task. And lastly, it scales well to things like image observations, because supervised learning, we know, works pretty well with things like images if you use deep convolutional networks. Okay, the downsides of this approach is it can potentially involve extensive human supervision, collecting a lot of data from a human. It won't necessarily, it will not outperform the human or the data that you collected. So this, without actually some reason about what performance is, it won't be able to actually do better than any of the trajectories that it saw. And lastly, this is best for domains where the human's control interface matches exactly what the actions that the agent wants to do. And there are situations where it may be difficult to collect demonstrations corresponding to exactly what the agent will do. And drifting, as I mentioned, drifting compounding errors can be a problem. So if you're interested in learning more about this area, here's a few papers, and my slides will be posted afterwards, and you can take a look at them. Okay, so how can we address some of these challenges with compounding errors and drift? Can we do better? And this is where reinforcement learning can come in. And in order to apply reinforcement learning, we need some notion of what success is, what is good and what is bad, such that we can actually optimize that metric with respect to our behavior. And this is where reward functions come in. Reward functions essentially tell us which state and which action is better or worse for our agent to perform. And so this was covered by Nando, but your reward function, if you have an example like this, you may have high reward because you're driving well on the road in a nice car. And if you get in an accident, then you have low reward. Okay. And the combination of your state space, your action space, your reward function, and your transition dynamics kind of capture this notion of a Markov decision process that our agents are operating in. Okay, so let's get into reinforcement learning. So Nando already covered a number of topics in reinforcement learning, but kind of the general anatomy of these types of algorithms is that you're going to be iterating between collecting data or generating samples in the orange box by running some policy, fitting a model or estimating the return of that data, and then using your model or using your estimate of the return to choose actions or improve your policy. And so a number of different algorithms you can view in this general framework. So for example, things like policy gradients are estimating the return. Things like Q-learning are trying to fit a Q function with dynamic programming. And things like model-based RL are fitting your dynamics function and using that dynamics function to select actions. And then once you fit some notion of your return or your model, then you use that model to compute actions or to improve your policy. In this lecture, I'm going to focus on model-based reinforcement learning algorithms, and I'll get to why we may want model-based reinforcement learning algorithms in the next slide. Okay, so why do we want model-based reinforcement learning? So the first reason is that oftentimes model-based RL can lead to better sample efficiency. And by better sample efficiency, I don't just mean like small gains in sample efficiency. In the literature, people have found that model-based reinforcement learning can often lead to 10 times or 100 times better sample efficiency compared to methods like policy gradients and Q-learning in some applications. And second, the model can often be reused for multiple different tasks. A policy is oftentimes specific for one particular task, whereas a model is just a model of the world, and with that, you can plan to accomplish different objectives. So what is kind of the key idea behind model-based RL? So you're estimating some model. We may use some parametric model F with parameters phi to try to fit that model. And the way that you can fit that model is basically just with supervised learning. So you can formulate some objective that is to minimize the difference between the predicted next state, given your current state and action, and the observed next state. Okay, so this is quite simple. And then once you fit your model, you need to actually figure out how to use it to optimize actions. So let's talk about the approach for optimizing actions. So one approach is to use backpropagation. So or some form of gradient-based optimization. So our goal is to maximize reward. And so what we can do is we can look at kind of the computation graph of states and actions to next states, and also states leading to rewards. And if our goal is to maximize reward, and we have a model of the environment, then we can simply backpropagate from the reward into the actions, choosing actions that lead to high rewards. And backpropagating the gradient from the objective shown on the left. OK, so this is quite simple. What this looks like as an algorithm is we first will run some policy. We then, to collect data, we then fit a model to minimize model error on that data set. And then we can backpropagate from the reward through our model into our actions. And this can allow us to choose actions that we can then execute in the world. OK, so this is pretty simple. Another alternative to gradient-based optimization is also gradient-free optimization. So another approach that you can consider is to optimize actions via sampling. And in this case, what you would do is the algorithm corresponds to running a policy, learning a model to minimize model error, and then iteratively sampling action sequences through the model to choose actions. And in particular, what this looks like is we could first sample a number of action sequences and run that through our model. Then we can get an estimate of a return, or each of the rewards at each time step for each of those trajectories. Then we can pick the actions that have the highest return, the highest sum of rewards over our horizon, and fit a distribution to those best actions to get a sense for what's the region of actions that maximize reward, and then resample from that distribution to keep on refining that distribution in that region of action sequences that lead to high reward. And then once you're done, you can execute the action sequence that has the highest return from your final distribution. And what this corresponds to is what's known as the cross-entropy method, or CEM, which is a gradient-free optimization method that samples these action sequences. And in practice, you could also use other gradient-free optimizers as well. And both of these, both gradient-based and gradient-free, are both reasonable methods for optimizing over actions that have different benefits in different situations. OK, so this is nice and simple. We learn a model, and then we use that model to optimize over actions. How can this approach fail? So one of the issues that will come up is that if your model isn't accurate everywhere in the state space, then this optimization can exploit any imprecisions in your model. For example, if your model thinks that if you are going to go straight, you'll actually go left, then, if it thinks that if you take an action to go left, you will actually go straight and get high reward, then your model will exploit that imprecision and choose the actions that it thinks will lead to high reward. And so we need to think about how we can actually overcome this sort of exploitation of the model. And as I mentioned with imitation learning, things like compounding errors can also come up where you make an error in one state, and then you get to a state that you haven't seen before, and your model may be even less accurate in that state. So one thing we can do is that if we find an action sequence that it doesn't actually, for which our model doesn't actually make correct predictions, then what we can do is simply add that data to our data set and refit our model using that data. And that will allow us to be more accurate in those transitions. And so what that corresponds to is we can just take the existing algorithm that we had before and then append the visited state action next state tuples to our data set, and then repeat this whole process where we then refit our model to that new data that we observed, and then plan according to that model, execute actions in the environment, see what result comes out, and then use that data again to update your model. So you get this form of trial and error that says, OK, I think that this path will solve the task. You execute that path. It may not solve the task, and so you add that back to your data set and use that to continuously improve your model. OK, so this can help you help the model be more accurate in settings where in parts of the data that you didn't see previously. And this is important for getting model-based reinforcement learning algorithms to work well. And so this will help. It won't necessarily solve the problem, though. In general, learning a model that's accurate in every part of the state space globally can be very difficult. And so another thing that you can do to do better is that instead of executing the entire action sequence that have highest reward in open loop, you can first execute the first action of that action sequence, observe the state that you get to, and if you get to a different state than where you thought you were going to get to, then you can replan action sequences again from that state. And so what this looks like is you execute the first action, and then you observe the next state and replan from that state. So what this allows you to do is that if you're planning and you take an action that you think was good but wasn't actually good according to the real dynamics, then you can look at that new state and correct for the error that you made on the previous state. And so this allows you to account for errors in your model and correct for them in real time as you're executing your actions. This is what's known as replanning. Another word for this is model predictive control, or MPC, which is really just a fancy term for saying that we're going to be replanning at each time step to correct for our model errors. OK, so this can work really well. And this algorithm in general is quite simple. We learn a model, we optimize actions for that model, and keep on optimizing it every single time step, and then use data from that, that execution to improve our model. Now, how well does this actually work in practice? So I'd like to highlight some work that was done by Anusha Nagabandi, who's a PhD student at UC Berkeley. And what she was trying to do is she was trying to enable a robot to manipulate these bounding balls. And in particular, the goal was to be able to rotate the balls in the palm of the hand. And this is a pretty difficult task because the robot has many different degrees of freedom in the hand, and it has to be able to learn how to do this without dropping the balls. OK, so this is what the policy looked like in the first 0 to 15 minutes of training. This is running something very similar to the model-based reinforcement learning algorithm that I showed on the previous slide. After 15 to 30 minutes, it gets behavior that looks like this. So it can start to rotate the balls in its palm, although it isn't able to do a full rotation without dropping it. After 30 to 90 minutes of training, it looks like this. So it gets stuck in this part of the behavior where the pink ball gets stuck in a notch on the top left, and it gets stuck here for basically an hour of training. And then after 2 hours, the robot is able to learn how to successfully perform the task. So it still has some challenges getting around that position, but eventually can figure out how to manipulate the balls into a circular trajectory. OK, so what approach was this actually using? So this was exactly the approach on the previous slide with a few modifications. The first modification is that it's using a probabilistic dynamics model instead of a deterministic model. So it's producing an ensemble of neural networks. The second is that it used used a sampling-based planning approach that was regularized to produce smoother action sequences. And lastly, it was using visual tracking of these balls to provide the state space of the robot and its environment. OK, cool. And so beyond this impressive demonstration of what model-based reinforcement learning can do, I mentioned that there are some benefits of model-based RL before. And we can see those in this paper. So the first is that the model can actually be reused for multiple different tasks. So if you train the model to write different trajectories with a pencil, or train the robot to write different trajectories with a pencil, can use that model for writing different digits on a piece of paper in simulation. And so these are different underlying reward functions that's able to perform with a single model, with a single approach. And the second is that it's significantly more sample efficient than model-free RL. So what this plot is showing is the x-axis is the number of data points that it needs to see during training, and the y-axis is the performance of this pencil drawing task. And what we see is that the model-free approaches are shown in blue and red, and the model-based approach in this paper is shown in the green line right here that learns extremely quickly, much more quickly than the model-free approaches. And this is why it's actually practical to run this algorithm on real hardware, as I showed on the previous slide. OK, so a quick summary of model-based RL so far. We looked at first a basic approach of collecting random samples, training a model, and then planning. The benefits of this is it was simple. There was no iterative procedure. But the downside is that we have this mismatch between the data that it saw during training and the data that it optimizes during planning. The next approach that we looked at was iteratively collecting data and refitting the model. This allows you to better learn a more accurate model in a bigger part of the state space, but it may still make mistakes with an imperfect model. And the last approach that we looked at was iteratively collecting data and also replanning at each time step to try to correct for model errors in real time. And this can make you more robust to small model errors, with the downside that it can be computationally expensive because you're performing this planning optimization in real time. OK, and then we also looked at 2 ways to optimize behavior with respect to your model, either backpropagating through the model into your actions or doing a sampling-based optimization. So next I want to talk about how we can do this in more complex settings where we have image observations. So before we had the position of the balls and the state of the robot's hand. What if we only have access to high-dimensional observations? So for example, what if we don't have access to this low-dimensional state S, and we have access to O instead? So for example, maybe we want a robot to use a spatula to lift up an object and put it into a bowl, and we can't directly observe where the bowl is or where the object is. And beyond this, we also don't have any reward signal that we can use if we only have the image. For example, if we have the position of the balls in the previous example, the reward function could be based on the position of those balls. Whereas in this case, the reward function needs to be looking at the images in order to provide signal for how to improve your behavior. So what we can do, one option for providing a reward signal is providing an image of the goal. So here we might provide an image that looks like this, that tries to show the robot, OK, I want you to lift up the object and put it into the bowl. OK, so there's 2 different types of approaches for this problem for handling images with model-based RL that I'll cover. The first is learning models in some latent dimension, and the second is learning a model of your raw observations. So let's first look at learning in latent space. So the key idea here is to learn an embedding of your images and then fit a model in that latent space. So if we look at this graphical model here, what we're going to try to do is learn a function that maps from O back to some latent state space and learns a model in that latent state space and does everything, the same thing as before, but just in this latent state space. OK, so there's 2 classes of approaches for trying to solve this problem. The first is probabilistic approaches that try to fit a graphical model to your data to learn some latent variables that capture your state. And the second is structured approaches that try to learn some spatial or object-centric representations of your state from your images. And so I'll go over both of these. And there's been a number of approaches in both of these camps. But I'll highlight a couple of the earlier works in this area. So one is a paper called Embed to Control, and the second is a paper called Deep Spatial Autoencoders. OK, so first, what does the algorithm look like? So we're going to be first running some policy to collect some data. We're going to then learn a latent embedding of our observation space, a latent representation of images, and a model in that latent space. So a mapping from O to S, and a model from S and A to S prime. We're then going to use our model to optimize over action sequences, and then execute the planned actions, append the visiting states to your data set, and repeat this process. OK, so there's 2 questions that come up here. The first question is, what is the reward function for optimizing actions? What you can do is if you have an image of the goal that you want to accomplish, then you can formulate your reward function as the negative distance between your embedded goal image and your embedded observation. And if your latent space captures a distance metric that accurately reflects how you want to accomplish the task, then this will allow you to perform goal-reaching type tasks where you want to try to reach the state underlying an image. OK, so this is one way that we can get the reward function. Now, how do we optimize the latent embedding space? So as I alluded to briefly before, there's these 2 camps. The first approach is to learn a graphical model or formulate a graphical model underlying your observation space. And in particular, what this work did is it formulated a graphical model over both your latent variables as well as a transition model over your observations. And so what this is doing is it's jointly learning the embedding space and the dynamics model inside that embedding space within a probabilistic graphical model. And the second approach that I mentioned, in this case, where we want to learn an embedding space that is structured, and in particular, the type of structure that we're going to try to impose on this embedding space corresponds to key points of objects in the image. So if we know that we want to manipulate objects, then it makes sense for our representation space to capture the objects that we want to be manipulating. So how can we go about doing this? Well, what we did here is we trained an autoencoder that takes as input the image and outputs a downsampled grayscale version of that image. And there's a bottleneck layer here that's trying to capture the latent representation. And what we can do to impose structure on that latent representation is take the last convolutional layer of our network, perform a softmax over the spatial dimensions of that image to get a distribution over potential key points for each channel. So this softmax can look something like this, where we're going to be exponentiating the activations and then dividing by or normalizing by all of the other activations in that channel. And then we can take an expectation over the 2D position of that distribution to get a key point corresponding to that feature map. And we can get different key points for different channels of our convolutional layer. And so this just corresponds to a linear expectation operation. And the result of this is we can get key points that look like this, that track objects and track the robot's arm in the scene. OK. And all of this is trained purely for reconstruction loss. So each of these operations are things that are differentiable that we can differentiate through to learn that representation. OK, so once we have this latent key point space, we can run model-based RL on those key points. So in this case, we initialized the policy with something that could match the arm position of the gripper of the task, but couldn't necessarily figure out how to get the object there. And what you see here is that through trial and error, it's learning how to push the Lego block to a consistent position. And here is a video of the final policy that it learned. My clicker keeps on. OK, there we go. And beyond this, we can also accomplish the task that I showed, or I alluded to previously, where we want to be able to learn how to lift up an object into a bowl. So in this case, it's learning the representation that I showed previously, and then running model-based RL to accomplish that skill. And then lastly, one of the nice things about this approach is that the representation, these key points are very interpretable. So you can actually plot these key points on the image and see what the representation is capturing. So you can see examples of the 2D key points on the image that are tracking things like the arm and the object. OK. Cool, and all of these skills were learned I learned using about 11 minutes of data on the robot. And this is the kind of efficiency that you can get if you use things like model-based reinforcement learning. OK, so the benefits of learning in latent space is that you can learn fairly complex visual skills very efficiently. And the structured representation, such as the key point-based representation, can enable very effective learning if you know the structure of the representation that you want to learn. The downsides of this approach is that if you're using reconstruction to learn your representation, that may not recover the right representation of your embedding space. So in the examples I showed previously, it was able to learn an effective representation. But as another example, one of the tasks that I wanted to try to get the robot to learn in this experiment was to manipulate something like a ping pong ball. So here's an example image of the robot and the ping pong ball that you can see in white. And I trained an autoencoder on a data set of these images, and the reconstructions that I got looked like something like this. So it learned to perfectly erase the ping pong ball from the image, and didn't capture that in its representation. And this was because the ping pong ball was very small, a very small part of the image. And so it chose the loss function corresponding to reconstruction didn't penalize that enough to learn the accurate representation for the task. So we have this disagreement between the objectives that are used for learning the representation and the objectives for performing the task. And lastly, the learned representations here were task-specific. So they learned a representation for those objects in that environment for that particular task. And this limits the ability to reuse that representation for multiple different tasks and multiple environments. OK, so kind of in general, we need better unsupervised representation learning methods that will allow us to learn representations for model-based RL. OK, so the second approach that we could use for learning with image observations is just to try to model directly in the space of images. So instead of trying to learn a latent space, we can actually learn a model over images. And what this corresponds to is modeling basically the same algorithm as before, except we're going to be handling observations instead of states. And we're going to be learning a model directly over observations that corresponds to a video prediction model if your observations are images. OK, so what this looks like is we might run some policy to collect a bunch of data. So you could collect data that looks like this, for example, where the robot is interacting with different objects in different environments. In this case, the policy is random. We can then learn a model to minimize model error in image space. So here are some examples of video predictions from a neural network video prediction model that are modeling what the future will look like based on the actions the robot takes. And this representation can also be used with things like deformable objects, because we aren't assuming any underlying object representation. We don't need to learn, we don't need to actually impose any object representation. It's simply learning to model the pixels. And lastly, you then use this model to optimize over action sequences. So a couple questions that come up here in how you actually, what are the kind of the details of this method? The first is, how do you predict video? Modeling video is a challenging problem. And the way that we did this in this work, and this has also been a very active area of research in the computer vision community, is to use a neural network architecture that looks like this. I don't want to go through all of the details, but kind of the key points are that it's a deep recurrent model. It's predicting multiple frames into the future. It is conditioned on actions. And it is, in this case, explicitly modeling the motion of pixels. So instead of trying to output pixel frames, pixel values directly, it's actually outputting how one frame will transform into the next frame. And this makes for an easier prediction problem for the neural network. OK. And then the next question is, how do we actually go about planning? So in this case, we're going to use exactly the same planning approach that I outlined before, where we're going to be sampling actions to and trying to sample actions iteratively such that we can find an action sequence that leads to high reward. And so, for example, if this is our image, we would consider a number of potential action sequences, hundreds of action sequences, including these two. We would then predict the future for each action sequence, looking at the predictions that look like this. Then pick the future that we like the best, that is closest to what we want to accomplish, and execute the corresponding action. And then lastly, you can repeat these first three steps to replan as you're executing the task. So essentially what this is just visual model predictive control, or visual MPC, where we're planning and replanning in pixel space. So the way this works is we collect the data set, and after we learn this model at test time, we can specify a goal. So the goal might look something like this. In this case, we're specifying goals by clicking on a pixel and clicking on where we want that pixel to move. We can then run planning with respect to that goal to find an action sequence that accomplishes that goal. So in this case, it finds an action sequence that picks up the shorts and manipulates it in a certain way. This is a video prediction, not a real video. And then we can actually execute those actions on the robot to get something that looks like this. And so we can see that the robot can figure out how to move the pixel successfully and somewhat approximately fold the piece of shorts. OK, and then one of the nice things about this, as I alluded to previously, is that we can reuse our model for multiple different tasks. So we can use it for grasping an object, for example, by specifying a goal corresponding to moving the pixel upward. We can use it for manipulating the sleeve of a shirt. We can use it for picking up an apple and putting it onto a plate. In all these cases, the underlying model is the same about how pixels will move, what the future images will look like based on the actions, and we just need to optimize over action sequences to accomplish these different goals. And so a few other examples are the shorts example, rearranging objects on a table, as well as covering an object using a towel. OK. Cool. So here's some examples of the kinds of tasks that we can do from image observations. And in summary, these models that try to model things in observation space can model fairly diverse scenes, more diverse scenes than the approaches that we saw before. And they can accomplish many different tasks with a single model. The downsides are that even though there is much more diversity in these scenes, there's limited background variability in kind of the environment that the robot is in. It can't yet handle as complex skills as the latent space approaches because these models are very large and hard to optimize through. And finally, this is fairly compute intensive at test time. So modeling in a low-dimensional space is relatively quick because your models are lower dimensional. But if you have a very large model that's modeling pixels and you're trying to replan it every single time step, that's much more computationally expensive. OK. I think I have some time. So one additional side is, can we think about combining imitation learning that I talked about at the beginning and model-based reinforcement learning? So what we can do here is we can take the approach that we were looking at before, where we collect data, learn how to predict a model using that data, and plan using that model. But instead of only using data from the robot's own interaction, we can also incorporate demonstration data. And we can use this demonstration data to expand upon the complexity of skills that the robot can learn. So for example, we can use this to improve the model by training the model also on those demonstrations in addition to the interaction of the robot. But we can also use it to improve the other two steps as well. So what we can do is we can use imitation learning to fit a model of the kind of behavior. And then after we use imitation learning to fit a model of the types of things that the human might do, we can use that to direct the data collection process by sampling from that policy to collect additional data that looks like the kinds of things that the human might do. And we can also use it to guide the planning process towards the types of behaviors that humans might be performing in those situations. So in this work, we were trying to look at, can we enable robots to learn how to use tools in different ways? So we collected data for using tools to accomplish different tasks. So here are some kinesthetic demonstrations of the robot, or demonstrations of a human guiding the robot to accomplish different things with tools. And then here are some predictions corresponding to samples from the action proposal model, samples from the policy that was fit to the demonstrations. And you can see that it can make predictions corresponding to grasping tools and moving them in different ways, and also grasping objects. OK, so the way that this works is the same as before. After we fit our model using both the interaction data and the demonstration data, we'll specify a goal. In this case, we may want to move multiple objects. Then the robot runs planning guided by the action proposal model fit to the demonstration data. And then we can execute these actions on the robot. So the robot can figure out that to move both of these objects to the left, it should grasp the tool and then use that to try to sweep the objects over to the left. And again, like before, because we're using this model-based reinforcement learning approach, we can use a single model for many different tasks. So we can accomplish tasks that the robot didn't see in the demonstrations, such as grasping a broom and sweeping objects into a dustpan. The robot can figure out how to use a hook to bring an object closer to itself. So in this example, we restricted the motion of the robot's arm to this green rectangle. And the robot can figure out that in order to bring the object closer to itself, it has to use the hook. The robot can also use tools that it hasn't seen before, such as a sponge to wipe objects off of a plate. It can use things that we wouldn't really consider as tools, like a water bottle to sweep objects over to the right. This is because we're not programming in what is a tool and what isn't a tool. It's predicting what will happen if it manipulates an object in a certain way. And lastly, you can figure out when to use a tool, for example, when it needs to push two objects, and when to not use a tool, for example, when it just needs to manipulate one object, and it's faster to just grasp the object directly and move it. Okay, so to review the things that I covered with regard to model-based reinforcement learning, kind of the key idea of model-based RL is to fit a model to our data using supervised learning, and then select actions by optimizing through that model by either backpropagating through the model or sampling. And there are a couple different approaches for correcting for model errors that include refitting the model with new data and replanning with model predictive control. And if we have raw image observations, we can approach this problem by learning a latent space, for example, with unsupervised learning methods, or by modeling and planning directly in your observation space. So it's worth mentioning, okay, we've talked both, at this event, we talked both about model-based learning and model-free learning. And so what are the trade-offs between the two of them? So some of the benefits of model-based RL, as I mentioned, is that it allows you to collect data in actually a scalable way without reward functions being labeled. You can learn a model just from your interaction. And it's also possible to transfer your model across different tasks. And also, it's typically more efficient than model-free methods. Now, some of the downsides of model-based RL is that they don't optimize for task performance. They're trying to learn a model. They're not trying to produce a policy that leads to they're trying to learn a model and then use that indirectly for performing a task rather than optimizing for task performance directly. And sometimes it's harder to learn a model than a policy. So for example, if you want to pour water from one cup to another cup, a model of the fluid dynamics of the water is much more complex than the policy needed to pour. And lastly, you often need some assumptions to learn complex skills like the ball task and the spatula task, such as assuming continuity and resets of your environment. Okay, so what about model-free? So the benefits of model-free is that it makes very little assumptions beyond having a reward function. You're just trying to optimize that reward function without trying to fit a model of the world. And it can be very effective for learning complex policies. The downsides of model-free RL is that it often requires more experience, so these algorithms are slower, and it's often not transferable across tasks if you're learning a policy to maximize one particular reward function. And it's, I guess, also generally worth mentioning that I think that we don't just want one of these approaches. I think ultimately we want elements of both model-based learning and model-free learning. Okay, so I'm going to put up some, beyond these pros and cons, I'm going to put up some suggested readings that you can look at if you're interested in reading more about this topic. And you can see these on the slides that are posted afterwards. So these include works that kind of use planning with a known model or do model-based RL with pixel observations. And so for some further reading, there's additional reading if you're interested as well. A couple references that I think are useful for learning more about this topic. Okay, and I'd like to lastly cover my outlook on some of the challenges in robotics and some of the kind of open problems that I think are most important to be working on in the future, especially if you're interested in kind of doing more research in this area. So in the long run, I think at least the question that I'm interested in is how can we build learning systems that are more general, that can accomplish many different tasks and learn and operate in the real world, in situations that they've never been in before. And of course, this is a very long-term goal, but I think that there are sub-problems that can help us make progress towards that goal. And one way that I like to think about this general problem is thinking about kind of one simple instantiation. So imagine that we have our kitchen, or maybe a kitchen that we haven't seen before, and we want a robot to be able to go into that kitchen and make a bowl of cereal. So this is like a very basic task for us, but this task is, it demands some level of intelligence and common sense about how to interact with the world, how to enter a new environment, search for things, manipulate them. Basically, a very challenging problem in the context of robotics. So what are some things that we need to be able to do to solve this problem? So one is the ability to convey goals to robots and for robots to understand what those goals mean. Things like being gentle or pouring milk. These are pretty basic concepts, but at the same time, they're things that are difficult to communicate through the techniques that we have right now. And so what current approaches do for trying to solve this problem is modeling it as an inverse control problem, whereas instead of producing behavior based on a reward function, we want to learn a reward function based on example behavior. So for example, you can learn reward functions from demonstrations that a human did guiding the robot, and the robot can learn to perform the task by inferring the reward function and optimizing that reward function. And you can do this both for putting a plate into a dish rack, as well as for learning how to pour from one container to another. And you can do this from demonstrations. You can also do this kind of approach from example images, where you want to learn how to drape a piece of cloth over a box. And so this is kind of where current approaches are currently at. But I think that this, demonstrations and example images are only one way to communicate objectives, and they're fairly limited because you have to be strictly in that environment, and you have to actually put the robot in those situations to communicate that goal. And ultimately, you want to be able to communicate from videos of humans doing tasks, from language, from text, by making analogies to other settings. I'm thinking also about how we can not just communicate one goal, but how these robots can reason about making progress towards kind of intermediate goals for making progress towards a longer-term goal. So here are some examples of kind of, I think, some of the challenges in this domain. Beyond the ability to convey and understand goals, there's also the notion of adaptability. So if you're in a new environment, you may not be able to perfectly generalize to that environment, and instead you want to be able to adapt your model very quickly with small amounts of data. And one, I think, very promising approach for doing this is by using meta-learning, by explicitly optimizing for fast adaptability. And by using things like meta-learning, what we can do is we can enable robots to collect data across a number of different terrains, then put it in a new situation, such as taking off the front right leg of the robot, and the robot can adapt its model of the environment in real time with very small amounts of data in order to run in a straight line. This is kind of one example of the kinds of very fast adaptation that we can accomplish. But at the same time, this is only a kind of initial step in this direction. And so we need robots to also be able to adapt to completely new tasks and also adapt visual models and visual policies to new environments. And then ultimately be able to handle kind of lifelong non-stationarity where the world is constantly changing. And along the lines of adapting to entirely new tasks, it's worth mentioning that we recently released a benchmark for studying multitask reinforcement learning and meta reinforcement learning. For some reason, the clicker is very sticky. That looks like this. It contains 50 manipulation tasks. And current methods really struggle on this benchmark and struggle to transfer information across tasks, even though these are all in a single environment with a single robot with kind of a single unified control interface. So I think that studying this sort of problem and this sort of benchmark is really important for addressing the current challenges with current techniques. And it's also worth mentioning that I noticed a poster earlier today that was developing a similar benchmark, but in the context of locomotion, where you want to transfer knowledge across different locomotion tasks and with legged robots in simulation. Okay, and then lastly, beyond the ability to convey goals and beyond adaptability is the role of data in robotics. So data, as we know, is critical for very broad generalization, and things like ImageNet, for example, have allowed us to learn very generalizable models of the world and of images, for example. But in robotics, we're kind of in this paradigm of setting up an experiment, collecting data in that experiment, and then fitting a model, fitting a policy, et cetera, in the context of a single experiment, rather than thinking about the rest of what the rest of machine learning does of having very large data sets like ImageNet. And as a result, if we look at the data sets that we use in robotics versus the data sets that we use in computer vision, the diversity doesn't compare. And so ultimately, I think that we need to be thinking about how we can accumulate and leverage very large and diverse data sets and have methods that can learn from data of this form. And so to try to make an initial step towards this direction, one of the things that we've been looking at recently is collecting a very large data set across different robots, across different environments, and actually across different institutions even, and studying how current methods can handle data of this diversity. And it turns out that current models tend to underfit and have challenges capturing the diversity and all the challenges that exist in this form of data. Okay, so that concludes things. I also wanted to link to other resources on reinforcement learning if you're interested in learning more. And a number of these resources have videos online, including lectures. And I'd be happy to take a few questions. Thank you.
There's a question over there.
Hello, thanks for your presentation. So it seems like most of these tasks are very easy for humans. So the question is, if you have seen or someone else is trying to understand how human does this task in order to maybe modify the algorithms to do it.
Yeah, so the question is, how do humans, do we understand how humans do this? And have people tried to look at how humans do this? Yeah, so people are certainly looking at how humans learn motor skills and how they perform motor skills. And actually, to my knowledge, in the neuroscience literature and in the psychology literature and cognitive science, there actually isn't a good understanding of how humans perform skills. There is some interesting research that has looked at kind of reaching type motions. And actually, motions are even simpler than the things that I showed in this talk. And I think it's kind of remarkably challenging to think about even how humans do these types of things. So I'm not an expert in neuroscience, but I think that from what I've heard on the neuroscience side of things, their understanding of how humans do these tasks is also very limited and something that we would love to learn more about.
Cool. There's a question over there, I think.
You could also shout, and then I could repeat the question, maybe. Okay.
So, from what I understood, the model-based methods, they try to predict the next stage given the agent actions. So, how do they deal when the state can be changed by other actions?
Yeah, absolutely. So the world's inherently stochastic. It is a deterministic process, and if you have other agents that are in the environment, then that may be increasingly stochastic because you can't directly observe the other actions of the other agents in your environment. The kind of general approach for trying to solve this problem is to build stochastic neural network models that can model and capture the type of the variation in what might happen in the future based off of their observations. So for example, being able to sample different possible futures that might happen as a result of the current observation and the current agent's actions. And so that's a pretty active area of research, especially in high-dimensional domains such as images that are trying to model this form of stochasticity.
Thanks. We have one question from the internet, very quickly, and then there's a question over there, I think. So the question is, how do you think we can use meta-learning approaches to improve data efficiency on RL problems?
Yeah, so a lot of my work that I didn't cover today is in meta-learning. And the key idea behind meta-learning is that we want to be able to leverage instead of learning from scratch for each new task that we want to perform, try to leverage our previous experience and learn priors about the world and about how to perform tasks from that previous experience. And I think that meta-learning is a very promising approach for doing that because it tries to explicitly optimize for the ability to quickly learn new tasks based off of that previous experience. And so we have a number of works on applying meta-learning to the reinforcement learning setting where we meta-learn models such that we can quickly adapt those models to new situations, and also meta-learn policies such that we can quickly learn new tasks. There's a number of challenges in applying meta-learning in these contexts, such as where do the tasks come from? Where do you get the distribution over tasks? And one direction that I'm excited about there is thinking about how the agent can construct its own tasks for meta-learning across, in addition to tasks that are provided by a user.
Cool. And let's take the last question.
It's working? Yeah. So in this field, how do people deal with situations where very high rewards are concentrated on very rare, very unlikely states? So for instance, car crashing, that's mostly unlikely.
Yeah.
So how do you deal with explorations of such situations?
Yeah, so this is quite a challenging problem, and usually kind of referred to as the sparse reward problem or exploration. One technique, I think one of the easiest techniques for dealing with it is incorporating demonstrations that show you how to achieve high reward. And this, if you have the ability to collect demonstrations and see some examples of how to get there, then that can make the optimization process and the exploration challenge much smaller. In the instance that you mentioned with driving cars, for example, in that case, you actually want to seek out the low reward regions and find those regions and be able to learn how to avoid them. And I think that in those settings, techniques like anomaly detection and adversarial robustness and distributional robustness are promising techniques for that, and being able to try to really find out those kind of very rare conditions, seek them out, and then optimize to be robust to them. And so that's kind of where things like distributional robustness and adversarial robustness try to do. They optimize explicitly for the situations where your policy will fail, and then tries to make it robust to those situations. That said, it's a very open area of research, and there's still a large number of challenges ahead for solving those problems.
Cool. Let's give a round of applause for Chelsea one more time.